Welcome back to the Unit 4 preparation. In this lecture we're going to be identifying chemical reactions, and it's the same reading in your textbook, page 254 to 259. And by the end of this lecture you will be able to identify the basic types of chemical reactions that we're going to be talking about in chemistry, both Chemistry 20 and Chemistry 30. So classifying chemical reactions, there's 5 basic types of reactions. And they're classified based on what we see happening in each reaction. So they are formation, simple decomposition, complete combustion, single replacement, and double replacement reactions. And using these types of reactions, we're able to predict the products of a reaction. So a formation reaction takes elements and makes compounds. So 2 or more elements form either an ionic or molecular compound. Either of these can be formation reactions, and the pattern that we're looking for is elements on our reactant side getting together and forming a product on the product side. An example would be magnesium and oxygen, and those are pretty straightforward. So the important thing with these reactions is that everything on the product side has to be in elemental form. So even though this is a diatomic molecule, oxygen always exists as a diatomic molecule when it's by itself. So all of the reactants are in elemental form. Decomposition is the opposite. It's going to take a compound and break it down into its elements. So it's the reverse of a formation reaction, and it involves a compound splitting into its components. And so we can have a compound, either a compound with 2 elements or a compound with 3 elements, and it breaks apart into its constituent elements. An example would be the decomposition of water. Notice that when it breaks apart, when water breaks apart, it's going to form hydrogen, but hydrogen is a diatomic molecule, so it has to form H2. Same thing with oxygen. Oxygen is a diatomic molecule, so it has to form O2, and then after, the reaction has to be balanced with coefficients in front. So even though they're decomposing into their constituent elements, elements that are diatomic form diatomic compounds as products. The next type of reaction would be a combustion reaction. Combustion reactions always involve oxygen as one of the reactants. If oxygen is a reactant, you can call it a combustion reaction. So, and for us, we're going to assume that all of our combustion reactions are complete. In reality, often they're not, but it's hard to predict some of the side products that are formed during combustion. So for us, all combustion reactions are going to be complete combustions. And the way we simply write the reactions, whatever this compound is here, it's going to consist of 1, 2, 3, 4, 5, 6, 7, 8 elements maybe. However many elements are on this side, each one goes and forms an oxide. There's an X oxide, a Y oxide, and a Z oxide. And the way we would determine what the compounds are supposed to be is based on this rule. If the compound being oxidized or being combusted has carbon in it, then CO2 is produced. If there's hydrogen in it, then H2O is produced. Sulfur, SO2, nitrogen, NO2, any metals that are in that compound form their most common ion oxide is produced. So for example, if we're burning, say, iron, or oxidizing iron, so iron plus oxygen, the way we determine the product is by ions. The most common ion of iron is iron 3+. So we're going to end up with Fe2O3 as the product. And then after, we go through and balance it. And so to balance our oxygens, we're going to have to put a 2 there and a 3 in front of our oxygen. That's going to balance our oxygens, which means we'll need 4 irons. So that would be how you balance the compound once you've determined what the product is. So some examples. The first example is even a little bit more special than just combustion. This compound here contains carbon and hydrogen, so it's called a hydrocarbon. And when we burn it, we do hydrocarbon combustion. And again, the products because there's carbon in our reactant, we get CO2 as a product. Because there's hydrogen in our reactant, we get water as a product. And then we balance it after. There's the iron example. For single replacement reactions, the general form is an element plus a compound goes to form a new element, and a new compound. And so basically what happens is whatever that element is, it switches spots with something in the compound. And so one way to write it is, at least in a general form, our first metal. So metal 1 and metal 2. Metal 2 is in a compound. After the reaction, metal 2 comes out, it becomes an element, and metal 1 takes its place in the compound. Or it could also be a nonmetal switching spots with another nonmetal. So here we have a nonmetal out of a compound or as an element, and another nonmetal in the compound, and they're going to switch spots. The nonmetal 2 comes out as an element, nonmetal 1 ends up in the compound. And some examples. For the first one, we have zinc as an element, silver in a compound, and so they're going to switch spots. So the silver comes out as an element, it's solid. When zinc goes in, because zinc is a 2+ ion, and NO3 is a negative ion, we end up with ZnNO3 2. And when we balance it, we note that we need 2 silvers for each, or a 2 in front of each of our silvers, and then a 2 that's applied to both nitrate ions. For the second one, here we're replacing hydrogen with sodium. One way to see this better is if we write hydrogen as HOH. And now here, this hydrogen is going to come off. It's going to form H2 gas. Notice because it's forming H2 gas, or because it's forming hydrogen as an element, it forms a diatomic molecule. And the sodium takes its place. So the sodium ends up with the OH. And so sodium hydroxide. Now, if we take a look, this reaction is not balanced, so we'll balance it here. And we'll take a look at our waters. And to balance this one, it does get kind of tricky, but when we write water as this HOH, it gets a little bit easier. If we take a look at our products, this hydroxide stayed together, so we're going to balance it as a separate ion. And we'll treat this hydrogen as being separate. So this hydrogen came out and became H2. So this hydrogen, on this side, there's only 1 on the reactant side. There's 2 on the product side. So for this, I'm going to put a 2 in front of my water. By doing that, I'm going to need 2 of my hydroxides now. So I'm going to put a 2 in front of my sodium hydroxide. And now I have 2 sodiums, so I can put a 2 in front of my sodiums. And now my reaction is balanced. If we take a look, I have 2 sodiums on my reactant side, 2 sodiums on the product side. I have 4 hydrogens on the reactant side. Here are 2, and then here are 2 more. This 2 is applied to the whole compound, so a total of 4. I have 2 oxygens and 2 oxygens, so my reaction is balanced. Double replacement is similar to single replacement, except everything's in a compound. So we're going to have 2 compounds, and a double replacement really means a switcheroo, if you like. The metal from one compound and the metal from the other compound switch spots. So metal 1 is with non-metal 1, after it's with non-metal 2. Metal 2 is with non-metal 2, after it's with non-metal 1. Okay, so for double replacement reactions, here's an example. Now if we take a look, we have iron nitrate, or iron 3 nitrate, sodium phosphate, going to form sodium nitrate and iron 3 phosphate. So what we're really seeing is here we have our metals, and they're switching the non-metals that they're associated with. So at the beginning of the reaction, the iron's with the NO3s. When we look at the products, the iron is with the phosphates. Notice that we balance it based on ion charge. Iron is a 3+ ion. Phosphate is a 3- ion, so they balance on a 1-to-1 ratio. Same thing with our sodium. Sodium is a 1+. Nitrate is a 1-, so again they balance in a 1-to-1 ratio. So when we determine our products, we do it using our ion formation theory. Then after, we balance using coefficients. So when we go to balance it, we see that there's 3 sodiums on the reactant side. So we put a 3 in front of our sodium nitrate. It turns out that nicely balances our nitrates as well. So we have 3 nitrates and we have 3 nitrates. 1 phosphorus or 1 phosphate and 1 iron, 1 phosphate and 1 iron. So we have a balanced chemical reaction. So let's look at some examples. The first one, we're going to predict the products and classify the reaction, and then we're going to balance it using whole number coefficients. So the first reaction here we have hydrogen and oxygen, and this would be an element plus an element. And so the one type of reaction we know that involves a reaction involving just elements would be a formation reaction. And formation reactions go to form compounds. So H2 and O2 go to form H2O. We know that water is a liquid at room temperature. And we can do this using ion formation theory if we like. Technically, it's not an ionic compound, and we should know what water looks like. But even if we used ion formation theory for this one, it would work. Hydrogens are 1 plus, oxygens are 2 minus, and so the 2 would come down here, and the 1 would come over here, and that's how we get our H2O. So this is a formation reaction. Note that we could also call it a combustion reaction. So this one can actually be classified as either, because it's a reaction involving oxygen. Now we're going to balance it. I'm going to get rid of my little scribble there over the 2. And to balance it, we're going to take a look, and we see that we have 2 hydrogens on either side, so those are fine. We have 2 oxygens on my reactant side, only 1 on the product side, so to balance it, we're going to put a 2 in front of the H2O, and because of that, we'll put a 2 in front of our H2 on the other side. So there's our balanced chemical reaction with whole number coefficients. For the next reaction, we have a compound reacting with oxygen. So this is definitely a combustion, because it's reacting with oxygen. Combustion reactions say that we take our compound and break it into its most common oxides. So we have nitrogen, hydrogen, and sulfur. And so what we're going to do, we're going to say, well, nitrogen goes to form NO2 gas when it reacts with oxygen. Hydrogen goes to form water. And sulfur goes to form SO2 gas. So we determine our products just by forming the most common oxides with each element from our compound in the reaction. And then after, we go ahead and balance it. And so we're going to start with the most common one and see how that works out for us. We're going to say there's 8 hydrogens on my reactant side. So to get 8 hydrogens on my product side, I'll need a 4 in front of my water. There are 2 nitrogens. So in order to balance my nitrogens, I will need a 2 in front of my nitrogen dioxide gas. I have 1 sulfur, so I can leave a coefficient of 1 in front of my sulfur dioxide. And now I'll check my oxygen count. The nitrogen, I'm going to have 4 oxygens. The water, I have another 4 oxygens. And at my sulfur, I have 2. So I have a total of 10 O's. And so to get 10 oxygens on the other side, I need a 5 in front of my O2. And now I have the balanced chemical reaction. So, whereas the first one could be classified as either formation or combustion, the second reaction is definitely a combustion reaction. Alright, so, same steps, different reactions. The first thing we're going to do is try and figure out what kind of reaction we have. And when I look, I see my first reactant is a compound. My second reactant is a compound. and we only have one reaction type that fits that description, and that would be our double replacement. So we got a compound plus a compound, and so what's going to happen is our metals are going to switch spots. So our silver is going to end up with the phosphate, and we're going to use our ion formation theory to figure out what the compound is going to be. Silvers are 1 plus, phosphates are 3 minus, so our compound, in order to have a balanced compound with a zero charge, it's going to be Ag3 PO4 1. Next compound that we have to make is zinc nitrate, and zinc is 2 plus, nitrate's 1 minus, which means we're going to need 2 nitrates to get a zero charge for our zinc nitrate. So it's going to be Zn NO3 2. When we take a look at our solubility table, we should see that zinc nitrate is aqueous, because anything with nitrate is aqueous. And for the silver phosphate, and for this one I'll actually have to look. The other one I had memorized. So for zinc phosphate, I'm going to find phosphate on my chart, and it turns out that zinc phosphate forms a solid, or it forms an insoluble compound. So this is, or silver phosphate, sorry, it's an insoluble compound, so we write a solid beside it. And so there's our two compounds, and now we're going to balance it. To balance this one, I can start probably with zincs might not be a bad choice, silvers aren't a bad choice either. I'll start with the silvers. I have 3 silvers on my product side, so I'm going to need 3 silvers on my nitrate side. And when I take a look, I can already see things aren't going to work out. Now I have 3 nitrates. Over here, I only have 2 nitrates. So in order for this to work, I can't use a 3 for my silver nitrates, because there's no way to balance out those nitrates. So I'm going to go through and I'm going to erase my 3, and we'll start again. So now I'll try and balance out my zincs. So starting with the silvers didn't work, and so as soon as you see it's not going to work, there's no harm in going back and erasing what you did and starting with something new. So here I have 3 zincs, so I'm going to need 3 zincs on the other side. This now gives me 6 nitrates, so I'm going to need 6 nitrates on my reactant side. Since I have 6 nitrates here, I'm going to get a total of 6 silvers. On this side I have 6 silvers on my reactant side. I'm going to need 6 silvers on my product side, and that nicely gives us 2 phosphates on my product side, and I needed 2 because I have 2 on my reactant side. So I'm just going to write this out a little more neatly, or attempt to anyway. Zn3 PO4 2, and you'll notice in your textbook they don't subscript the states, so if you don't subscript your states, that's okay. I tend to, just because that's the way I learned to do it, so it'll take a while to change, I think. So there's my reactants. I get 2 Ag3 PO4, and that's a solid, plus 3 Zn NO3 2, and that's aqueous. So there's our balanced chemical reaction. I don't know if it's any neater or not, but that's what we're going to do. The next reaction, bromine and calcium chloride. And here we have an element reacting with a compound. And again, we only have one type of reaction that fits this description. It's a single replacement, and the thing that is the same, or the type of chemical, how do I want to say it? The type of chemical that gets replaced has to be the same kind that's replacing it. So here we have a nonmetal. It's going to replace the nonmetal in our compound. So we're going to end up getting Cl2, and it's going to be a diatomic molecule because chlorine forms a diatomic molecule when it's by itself, plus CaBr2. And again, we get the CaBr2 just by using our ion formation theory. Calcium forms a 2 plus ion, bromine forms a 1 minus ion. So that's how we get our balanced formula, and this is going to be aqueous once we check our solubility table. So there's the balance, or there's the chemical reaction. Sorry, we want to make sure this is official. This is officially a double replacement. This one is officially a single replacement. And now to balance it, I think we're good. If we take a look, we have two BRs on one side, two BRs on the other, one calcium, two chlorines, two chlorines. So we're good. We have a balanced chemical reaction. It turns out we don't have to put any coefficients in front, and that's okay. It just means this one was easy. And for our last reaction, here we have a compound, and here we have an element, but more importantly it's oxygen. So this is going to be a combustion reaction. And so, same steps for combustion reactions. Each element forms its most common oxide. So, we're going to have a nickel oxide and a sulfur oxide. Now, nickel is a metal, so in order to determine the oxide formed, we take a look at our periodic table, and we see that nickel's most common ion is nickel 2+. It's going to react with oxygen to form a compound with zero charge, so since nickel is 2+, oxygen is 2-, our compound is going to be nickel oxide. And we know it's solid because it's an ionic compound. The other product is going to be SO2 gas. So sulfur forms its most common oxide as well. Notice that when I'm writing these equations, I leave lots of space in front of each compound in order to get room for my coefficients. So just out of habit, it helps if you leave some space in front of each compound so that you don't have to squeeze your coefficients in. You have lots of space to put them in after. And so our nickels are good and our sulfurs are good. So we're going to have to balance our oxygens. On my reactant side, I have 2. On my product side, I have 3. And so the way to balance it is we're going to go with 3 halves. And by doing that, 3 halves times 2 will give you 3, and now my equation is balanced. But we want to use whole number coefficients. So the way to get rid of our fraction is by multiplying the whole equation by our denominator. So we're going to multiply this whole thing by 2, and when we do that, we end up getting 2 NiS, or 2 nickel 2 sulfides, plus 3 O2 gas, 2 nickel oxides, nickel 2 oxides, plus 2 SO2 gas. And now there's our balanced chemical equation with whole number coefficients.